Good morning, Calculus 2 students. Well, I guess, like I said on Monday, we're back into springtime, and I'm not going to complain. Um, I'm thinking, as most of you all are future STEM professionals, uh, you may get into the energy sector and work with states like Texas to weatherproof their electrical grid. I mean, there are all kinds of engineering jobs that require good STEM professionals. So that might be another thing that would pique your interest. Um, Texas has a very refined electrical system that uses all types of sources, but when we're encounter weather that just goes so far beyond the scope of what we even think of having in this state, it can pose many problems. And so that's what STEM professionals do. They solve problems. And with that, um, we're going to have another test coming up next week. If you look at the schedule, it's going to be shorter, that's better. And it'll be the same type of examples that we had on the first test with the new ideas with the integration. If you look on Blackboard for the test work, there will be numbers there that support any partial credit points that you were awarded. And then, of course, your test grade was adjusted by those. In some cases, the partial credit points were negative. It is important, and I've said this before, your work must support the answers that you choose. And I was lenient this time. I was very pleased that most of you presented work that I could read, that you scanned it and it was legible and I could follow your work. If you present scans that are very tiny and blurred and I cannot read them, then that is an issue. So make sure before you send or upload your scans on Blackboard to the Turnitin that when you look at what you're sending me, you can actually read it. That's very important. And so I respect all of you as future STEM professionals, but remember, calculus is the bedrock of what you will be doing. And it requires more time than most of the classes you're taking right now. And so you need to spend good quality time every day on this course. There is no substitute for that. All of my past students, again, that have gone on to complete their engineering degrees, complete master's degrees. I've got two students right now, as I've said before, working on PhDs, one in biomedical engineering and one in computer science. And they all focused on the math because the math is your language as a STEM professional. So I have complete confidence in everybody that you will put in the time and watch the lectures, study the test solutions, study the lecture notes, do everything you can to practice as much as you can. My lectures give you the blueprint. I should be able to look at your work and follow what you're doing, not you write something down and then magically you have an answer. When that happens, that's telling me that there's maybe not a whole lot of honesty going on with the test. If you're using computer algebra systems to get to an answer, then you need to stop that. Integrity comes from doing your best and then making a selection based on what you've done. So please be aware of that. I want you to get to the university prepared, but you will not be prepared if you are depending on other gadgets to get you through a class. That is not what we do at San Jac. At San Jac, we have a very high academic level. And if you read the Blackboard policy about our academic standards at San Jac, it is very clear. So please abide by that and take advantage of my conference hours. I have one today. I have three tomorrow. I have one on Friday. So I enjoy when you all come by and we can work problems or send the WebAssign messages and I will help you, send you solutions, whatever. Just make sure that you're spending time on this class every day. That is very, very important. Okay, so again, like I say, in the future, some of you may be working on the electrical grid in Texas, and that'll be a marvelous thing. So that means we'll have smart Sanjak students paving the way to energy independence in Texas. Okay, so what we want to do today is continue with the trig integrals. Remember, last class I said something about cosine squared. And I said, okay, we could do this integration by parts. And then I said, well, what if we just say, okay, integration by parts, it was algebraic, it was a little bit long. What if we used a trig identity? And that made the problem a little bit more accessible and quicker. Now, what we're going to find today, as the powers get higher and higher, that technique may not be as good. And so we can often use what are called reduction formulas, which are based on integration by parts. So I want to start the lecture with a reduction formula. So what we're going to say, let me just give you the title of it, reduction formula. So when we think about powers of sine, cosine, products of tangents, secants, cosecants, cotangents, we think about identities, and identities help us quite a bit. And plus, the technique that we just learned, integration by parts, helps us even more. So here's an example of the first reduction formula. We're going to let n, for n 2 or greater. So basically, n will be a natural number. So we'll say n is a natural number, 2, 3, 4, like odd, even and odd positive integers, counting numbers, no fractions. So for instance, sine of u raised to the nth power, using our shorthand notation, because of course in math we're lazy. We don't want to have to write so many parentheses, du. Now, this is called a reduction formula because you actually prove this with integration by parts. And so I want you to put these reduction formulas on note cards. You're also going to find them in your integral tables in your ebook, but I want you to have these access to these to use. So we're going to have the additive inverse of the n minus first power of sine u times cosine u divided by n, plus n minus 1 divided by n, that's the coefficient based on n, the integral of the reduced sine power, reduced by 2. So what we see here is that this would even work for sine squared if we didn't want to use the trig identity, the power reducing trig identity. But what's nice about this formula is that we can actually verify it using integration by parts. And I'm going to do that, but first I want to do an example. So notice here, we figure out what the n is, and then we write this down with the n's included. And whatever u is, if we have to make an adjustment for the differential. And then once we get here, if this is simple enough, we're like, okay, that's just turning out to be a constant, so we can integrate that and that's easy. Otherwise, we take this formula and we apply the reduction formula again. Now, you might be thinking this is inductive. It's not, because this doesn't work for all natural numbers. This is just a recursive property or formula that we verify with integration by parts. So let me give you an example here. I just made this one up. And say we had the following problem. 0 lower limit, pi over 6 upper limit, and we have the fourth power of sine 6x dx. Okay, so if you look at this, ladies and gentlemen, you're thinking, okay, well, I could put in the power reducing identity, square it, and then collect my terms and then integrate trig integrals. Well, I want to show you that the reduction formulas give you an opportunity to actually do the computation in a very efficient manner. So this is what I want to impress upon you today. There are many ways to do these types of integrals. And of course, if we just have plain old sine square, we use the power reducing. But I found when I have taught this course that students that use these have more accuracy. Now, remember, as you use different techniques, the responses will look a little different, but they will be equivalent. That is, when you work with them, you'll show that they actually are exactly the same or differ by a constant, which is the mean value theorem. So again, remember, we want techniques that we can learn, but we want techniques that are doable and not so heavily tedious that they become a burden. But sometimes the burden is all we can, live with. So now what we're going to do is be very Calc 1. We're going to change out everything and make the problem very, very simple. So notice U is 6x. So we're gonna even do better than table ready. We're just gonna switch everything out like we're doing miscellaneous. And du is 6dx. So that means we're going to need a 6 here and a 1/6 outside. And while we're at it, because we want to use this, we're going to go ahead and change the limits. So u of pi over 6, again, that's just going to be pi over 6 times 6. The 6's will absorb. And that leaves us with a pi. And then, of course, u of 0, well, we just put in 0, we get 0. So those are our new limits, just to make the problem a little bit easier. So now what we're going to do at first is do the table ready bit. So we're going to have the 1/6, 0 to pi over 6, sine to the 4th, 6x, and then put in our adjusted differential. So now this is table ready. There's our du, that's our sine of u raised to the 4th power. And then now to switch it out completely, because that'll make the use of this formula much easier. Lots of times when we do table ready and we stay with the original variables, that's fine, but it's a little bit more subtle. And I find that students tend to do a lot better when I use this method when we switch things out. So we're going to do that today, but feel free to use whichever method. I just want you to be comfortable. So now we get 1/6. The new lower limit is still 0. The new upper limit is pi. And now, of course, we have sine to the 4th u, and then, of course, du. So now this is good to go. It's a definite integral and we don't care about anything else anymore. We have transformed this into a nice, neat package that we can now apply this. So this is very important. I want you to put these on note cards. I'm going to give you 5 more to cover all of the 6 trig functions. I want you to put these on note cards and use these. So this is n equal 4. Some of you may just go ahead and commit them to memory, but no need to do that. If you were in a face-to-face class, I would write these on the board because I want you to be able to show me that you can use the formula. I mean, I know you remember the Pythagorean theorem, but this is a little bit more complicated. So now n is equal to 4. So now all we do is just fill in the formula. So remember, we're stuck with this 1/6, okay? So don't forget it. It's on the outside, so you remember it. Just drag it down, put in a bracket. So let's go to the first term. So we're going to have the negative of sine. Now we have 3u cosine u. N is 4, so we have a 4. Evaluate 0 to pi. That's this piece right here with these limits. And now the integral part will just be 3 over 4. And now we reduce the power of sine by 2. So we have sine to the 2nd power. That is sine u to the 2nd power, limits 0 to pi du. Now what could be easier? The reduction formula uses the power of integration by parts, but you don't have to do the integration by parts. You let the integration by parts give you the reduction process. So now you can see we've simply filled all of this in with the appropriate ends, and then of course with the limits that we need, and we have our 1/6 factor on the outside because of the differential. Okay, now we just go about doing what we do in Cal 1. We're going to apply the formula one more time. We could use the power reducing identity here, but let's just go ahead and apply this one more time since now, and I'm going to write this in for the next integral, n will equal 2. So just remind yourself that's what we're going to do when we apply it a second time. So now for this part, go ahead and multiply by the 1/6. So we have 1/6, and then the 1/4, the negative, we can just go ahead and bring out negative 1/4. And if we evaluate, this is a really, I picked some really good limits. Notice sine of pi is 0. So that zeroes out the first, the term here with the upper limit. And then of course, if we put in 0 for the u, sine of u is 0. So I chose this so the arithmetic would be a little simpler to get the point across. So notice when we supply or substitute the pi, of course, cosine of pi is -1, but this is 0. So the first application of the upper limit gives us a 0. And then when we substitute 0 here, the sine of 0 is 0. So lo and behold, 2 zeros. So we're, happy face with that. Okay. Now remember, we have 1/6 times 3/4. So plus 1/6 times 3/4. And we have now, again, we're going to apply the formula here. Let me just go ahead and put a box around it. We apply the formula here again. So apply reduction formula. Do it one more time. N equals 2. So we've got the 1/6, the 1/3 bracket. Go up here and fill it in. We have minus. So we get 1 sine to the first power of u, cosine u, and n is 2, and then of course 0 to pi. Again, those are going to zero out when we don't have any problem with that. And now notice we've got the 1/2 integral 0 to pi. But now notice with 2 here, we get sine to the 0. So that by definition is 1. So we're just left with du. So you're seeing this reduction formula is super simple and super efficient. And isn't it nice to be able to do an integral? I know you all get confounded with doing those application problems because the arithmetic is challenging, and a lot of you struggle with it. It's not your fault. You just not used to it, and it's okay. You're going to get a lot better. I do have some of you who are working very hard with the mathematics and the arithmetic, and I applaud you for it. Everybody just keep working. You will get better. Now look, we just have to finish this off. The reduction formula has made a very tidy process of this integral. So now, of course, this just zeroes out. So we just get the big 0 plus. Now notice here, we can go ahead and configure the 3/6. That's going to give us a 1/2 and the 1/4, but go ahead and write it down. And now we're going to get a -1/2 out of this, -1/2, but maybe you don't even care, because now when we substitute again, the sine of pi will be 0. So the upper limit will annihilate like it did before. And the lower limit, sine of 0, will annihilate. So good for us. And then the very last one, if you want, we've got plus. I'll go ahead and put the 3/6 so we can see that they absorb. Write everything down so you can always go back and check your work. Otherwise, you come to grief. Okay, so now easiest antiderivative in the world, which is just plain old u. evaluated 0 to pi. The thing about the reduction process is that you have to remember all of the constants and keep multiplying them through. Keep track of them, or if you keep the brackets, just make sure you don't forget about these constants. And so now what do we have left? Well, of course, this is a 1/2 times 1/4 times 1/2. And then, of course, here we just get pi minus 0. This is the only one that just doesn't zero out, pi minus 0. So now here we have 4 times 4, so that's 1 over 16. And this, of course, is just pi, so we get pi over 16. Now, I can assure you that this process is quick and efficient. If you were to do this with the reduction formulas, by the time you did all the algebra, you would have probably made 3 or 4 mistakes and gets a ridiculous response. And that's what I sometimes get tired of, seeing my students struggle with algebra. You get anxious, you want to get to the finish line too quickly. And of course, we've all been there. So the idea is, what I'm thinking about is that if you go ahead and think integration by parts and use the reduction formula, which Dr. Larson does teach in this section, I think you find that you have a process that's very efficient, very clean, and easy to use. Now, of course, you have to take a little bit of time to get used to it, but it makes this problem very, very straightforward. Now, I have students that live in both camps. Some of them like the power reducing, some of them like the reduction formula. So it's about half and half. But I think last semester, we tried the reduction and most students were okay with it, but they struggle with the algebra. But I don't think you have much to struggle here. So it's a very straightforward process. Now, what I want to do, I'm actually going to show you why this is true, so you can really see that this is a bona fide technique. But before I do that, ladies and gentlemen, I want to give you the 5 other reduction formulas that you can have to put on note cards. Okay, so know how to do this. This is a nice recipe for the reduction process. All of them will be done this way with this kind of format. Now, I have these others written, so let me go ahead and give them to you. I thought maybe it'll just be good to go ahead and give you the other 5. So let's start with 2 with the cosine. The cosine is very useful because it helps us to prove the Wallace formulas. We don't prove everything. We just want to make sure that what we're using is legitimate. So for cosine, again, this will be n greater than or equal to 2. We'll have cosine the nth power of cosine u. And this looks like the last one. This is cosine n minus first power times sine u over n. So it looks just like the last one, except we had a negative and this was the sine and the cosine were interchanged. Then we have the plus n minus 1 over n. This looks the same, of the n minus second power of cosine u du. So this one, if you compare, you can see how it's very similar to the sine, very similar, okay? So again, remember here that what we strive for in calculus are effective methods to integrate that we can do that don't derail the process. That's what we're looking for. Now, I'll give you the tangent next. You can find all of these in your integral table. This is how I introduce using an integral table before we actually get to it. So let's do tangent u, the nth power of that. And this will be the n minus first power of tangent u, a little bit different, divided by n minus 1, can be proven the same way as the one we're going to do with the sine, minus the n minus second power of tangent u du. The idea here is that we're not really concerned about tangent to the first power. That's ridiculous. We don't care about that. We just start with 2 and bigger where it really is going to make any difference to us. So again, the tangent, let's go ahead and do, I'll go ahead and pair with this cotangent. Again, the same n greater than or equal to 2. I had a student one time, Professor Ron, isn't it just n greater than or equal to 2? I said, exactly. But of course, the math gurus are going to say you can use 1, but you know, when it's undefined, clearly it doesn't make any sense. So we'll just stick with this. So cotangent n nth power look very similar to this. We'll have the negative and we'll have the n minus first power of cotangent u divided by n minus 1. And then again, the integral's kind of naked. There's no nice coefficient out front. So don't be bothered by that. Some easy is good. So notice these are very similar. In both cases, we have a minus here in front of the reduction integral, and then we have the n minus first power divided by n minus 1. So they look similar. Now let's do the secant and the cosecant. Now you already know the integral of secant cubed, don't you? We did that integration by parts, so you could actually use that for this. But we've already worked that through and made a nice tidy formula, so we're gonna stick to it because we don't want to overwork. So the nth power of secant u will be secant n minus second power u tangent u n minus 1, all embedded using the Pythagorean identities, and then n minus 2, n minus 1, this n minus second power of the secant u du. Again, n greater than or equal to 2. So these are ones that are the most busy, but again, these vary a little bit. So we have the n minus 2 power of secant times tangent divided by n minus 1, and then n minus 2 divided by n minus 1, the n minus 2 power of secant. So these reduction formulas are a little bit more busy. And now the cosecant power looks similar. This one goes like this. We have the negative of the cosecant n minus second power times the cotangent. You can see how they are very, they just parallel n minus 1. And then we have the same coefficient here, n minus 2 over n minus 1. And then we have the n minus 2 reduction integral power like we had before. So with these, and as I run through these, like I say, I took these right off the integral table, and let me just make sure that everything is exactly the way I want it, because I want these to be, and you can also reference, if you like, the integral table in your ebook to check these. And then the secant, this looks good, and then the cosecant. So these are the reduction formulas which will assist you with powers of cosine, powers of tangent, powers of cotangent, powers of secant. I mean, if the powers are relatively low, you can just say, all right, I'll just use Pythagorean identity and move it forward. But the issue here is that when the powers get higher and higher, you need a method that's a little bit more efficient. And Dr. Larson does a nice job of presenting these in this section. That's why this textbook is so well received. It's an excellent book. Okay, so now let's go back and look at why this formula for the sine is true. And then if you like, you can try it out on some of these. You'll have a technique, and just try it, just for fun. I won't test you on this, but I do want you to know how to use them. So let's look at this. So here's our formula. That is, we have so we'll just say justification or proof. Justification. So proof. Basically, when we think about an integral formula, it's like, why is this true? Justify why this is a valid formula. So we have sine nth power du So let's just remind ourselves what it looked like. We had the minus sign n minus 1 of u, the n minus first power, cosine u divided by n. And then we had this interesting coefficient n minus 1 over n, integrating the n minus second power of the sine. So in this case, we have sine n minus 2 power du. So the idea here is that if we think about this as an integration by parts like we were doing cosine squared before, we do it the same way. So let's break it up. So now we'll have this integral, sine the nth power. What we want to do is just remove one factor and apply integration by parts, and we'll do it the standard way. So we have sine to the n minus first power of u, and I'll put a little dot here to make it real clear, sine first power of u. So the idea here is that since we're using u's and, in the formal way we use u's, I'll use the D column and the I column. So what we want to do is say, okay, this would be very simple to differentiate, and that would be our choice to differentiate. Obviously, that's just as hard as that integral. So we would never want to integrate that. That makes no sense. So we would say D. So we pull off this to differentiate in our informal tabular form, like this. And you don't have to make an assignment since we're already using U. You know how to do this. And so here, we'll do our integrating column, basically our dv. So that's just going to be the sine u du, but we'll just put the sine u. I don't want to just create a bunch of new letters since we're already using u just to cloud the situation. So just remember, you always pick something to differentiate. You always pick something or a factor to integrate, always. Okay, so now we can apply the chain rule here. So now you're going to see where the n minus 1 is coming from. Okay, so this will be n minus 1 times sine n minus 2 power times the derivative of sine, which is cosine. So when you look at this, you're thinking, well, that's simple enough. I've got my coefficient, I've got my n minus 2 power of sine. The chain rule gives me the derivative of sine, which is cosine. We're good to go with that. Now, the integral of the sine, of course, is the negative cosine. So we don't have to do anything to make it table ready. Okay? So now this is integration by parts. So we do the product, the quote unquote u times v, right? And then the v du with the integral, again with the minus sign from our formula for integration by parts. Okay, so now what does this equal? Now, I will already tell you, you know this is going to be algebraic. This will be algebraic. The integral will actually repeat. And so this is going to be an algebraic method. So now we have the negative cos, look, there we go. We got the negative, and then we'll eventually get the n. So I'll just write it in the same order. Negative sine n minus first power u cosine u. Okay, the product of these two. So we're already kind of seeing the end of the process even at this early stage. And then we have minus minus. So that'll be a plus. So we have plus, and let's go ahead and factor the n minus 1. So we're already starting to see these coefficients. So we have the n minus 1, which is a constant. And now we have the sine n minus second power of u. And note here, we have 2 powers of cosine, and so that gives us a cosine squared. Now, the thing is, in order to prove these, we have to use the Pythagorean identities. So embedded in this process is the Pythagorean identities. And so you can't do one without the other. And so when you think about this process, it takes care of all of the tedium and then delivers a nice formula that you can easily use. So now when you look at this, you're thinking, well, how do we move this forward? Well, we're going to get the original integral by replacing this with 1 minus sine squared. So now we get negative sine n minus first power, and then we have plus n minus 1 sine. It's like we're in trigonometry all over again. So we have 1 minus sine squared, just by the Pythagorean identity. Okay, so now you can see that when we multiply this, we're going to get a n minus 2 power of sine, and then of course an nth power. So we're going to repeat the original integral. So now you see this is also algebraic. So let's write the next line with the two integrals broken up, or the one integral separated into two using linearity. After you do a lot of calculus, you just assume all operations are linear, but they're not. So you have to be careful not to assume linearity when it makes no sense. So now here we've got the sine n minus second power times 1. So we're getting something that looks like that. And then secondly, we have the sine n minus 2 plus 2 gives us n. That's also multiplied. But notice in this case, ladies and gentlemen, we have a negative. So now we get minus n minus 1 sine nth power of u du. Again, where this repeats, accepting the constant, the original integral. So now we're going to move this over, okay? So now we're going to add this. So now we're going to have 1, that integral, just put a 1 in front of it, plus n minus 1. That's going to give us the n that we need, times the original integral. And so this gives us negative sine n minus first power cosine u plus n minus 1 sine n minus 2 u du. So the idea of the reduction formula is that it would be insane to do this every time. You do it once, it's just like you use the quadratic formula. Do you derive the formula every time you use it? Of course not. So you think, okay, I'm going to do this once and then I'm going to use this. That's called good mathematics. We don't want to do extra work thinking that's going to make us better. We do the work that is necessary to solve the problem, but we don't want to do excessive work if we have a method that's more efficient and gets the job done with less mistake. So now you can see that when the 1's absorb, this is just an n. So now we can divide by n and we get this formula. So equivalently, it really wasn't so bad to justify or prove, but we do this once and then we're done with it. So now we can divide by n. So we have this term here. And then, of course, we divide this coefficient by n to get this term. Which is what we wanted to show. So this is why I spent quite a bit of time on the integration by parts. That is something that you must master. You must spend quality time on integration by parts, and I give you plenty of good details to do it. Do not, under any circumstances, underestimate the validity and the usefulness of that process. It is very important, and you should spend plenty of time on it to master it, because it will help you. Every time we learn a new technique, ladies and gentlemen, we get that much better at the previous ones. And when you go back and rework them, it's like, wow, the light bulb has come on. I actually know what I'm doing. So the beauty about math is like studying any language. You take more Spanish or more French or more German or whatever, and then you think, oh, how could I ever do anything until I took Spanish 3? Because I didn't know anything. Then you go back and look at Spanish 1, and it all just is illuminated in a way that you never saw before. So math is the same way. So again, if you want, you can try this out on the other formulas that I've given you, okay? And use the reduction formula kind of as a clue as to how you need to set up things like we did here. That's the thing that we do with integration by parts. We have to figure out how we're going to pick the U and how we're going to pick the DV. That's the technique. And sometimes we don't make a good selection and we start over, but that's okay. That's what we do in math. Okay, now, ladies and gentlemen, I want to give you some results by a mathematician named Wallace. Wallace, I love what Dr. Larson does. He has all these little historical blurbs in his text. And Wallace did calculus basically before Leibniz and Newton were credited with its invention. And he came up with some nifty formulas. These trig integrals, most of you will see again when you study Fourier analysis, when you take partial differential equations. And this material is extremely important. You'll tire of it maybe, but you will definitely appreciate your pre-cal class for learning trig. So let's look at some interesting formulas that can be proven using the reduction formula for the cosine. But I want you to be able to take advantage of them. They're called the Wallace formulas. Now, what's interesting about these are valid for sine and cosine. I'm just going to write them with cosine. They're valid for sine and cosine. So we're going to have powers of sine and cosine. You can interchange them, you get the same answer. Now for the first formula, again, this is a formula which is for a definite integral. N is odd. So we're going to say 3, 5, 7, 9, etc. N is odd and at least 3. And we're going to do the integral from 0 to pi over 2. This is a specific definite integral of the nth power of cosine. So you're thinking, oh, I see, Professor Ron. This is where you use the reduction formula for cosine and you keep applying it until you exhaust the power. And this generates the formula, just like I did on the first exercise. Remember, we did a definite integral, but it wasn't 0 to pi over 2, so it didn't apply. It was 0 to pi over 6, but I could have rigged it so it would apply this way, but I thought I'll make it even easier with pi since everything's zeroed out. But here, what we're seeing is that this is going to generate a formula just like we did with all those factors. We had all those fractions multiplying. That's exactly what this is going to do. So when we look at this, we're going to think n minus 1 over n, which we get from the reduction formula for cosine. So this is going to give us the following. 2/3. And then we're going to bump up to the next even number and then the next odd number, 4/5. Then bump up to the next even number, the next odd number, etc., just like that. And I'll just do one more. This is kind of overkill, 8 over 9. And you just keep going until you exhaust and end with n minus 1 over n, which is that factor that you see in the reduction formula for cosine. So you figure out the n and you ascend to as many factors as you need, boom, there's your answer. So you can see how the reduction formula justifies this numeric formula by Wallace. And again, this is also good for sine. If you switch out the cosine with sine, you get the same answer. Now 2, n is even. And of course, because this is even, this is going to carry a pi symbol in it because we can't get away from it. With the even, we're kind of forced with that last power giving us, when we go from 2 down to 0, just like we did with the sine to the 4th, we're going to be stuck with a multiple of pi. So unlike this one, which has no pi, the even power will have a pi. And so in this case, n will be greater than or equal to 2. So we're going to say 0 to pi over 2 cosine n. Again, these look exactly the same, but in one case, n is odd, and in the other case, n is even. So now you know you're going to start with a 1/2, and then move the same way. 3 over 4, 5 over 6, and then 7 over 8, etc. And then you ascend to the last factor, second to last factor, n minus 1n. And then, of course, you're stuck with the pi over 2 like we were stuck with the pi in the problem I did first. So remember, we had pi minus 0. Here you're going to get pi over 2 minus 0. So boom, pi over 2. I remember I always have a student say, well, why does that one have a pi over 2? And when I explain it, oh, I get it. So the reason is that when we looked at the first example here, you just get these cascading factors here. And so you're stuck you're stuck with the pi here like you get stuck with the pi over 2. So what Wallace did, he just said, okay, well, I'm seeing this pattern over and over. And he developed this. He developed this before Leibniz and Newton's basically codified calculus. See, Leibniz and Newton understood the connection between the antiderivative and the derivative, that is the area calculation and the tangent line calculation. They were the first ones to write down the fundamental theorem, okay? Many other people did calculus and they understood its value, but they did not write down their results in a codified way to allow them to receive credit for its invention. So just remember, there were many, many, many people who helped to develop the calculus. And after Leibniz and Newton, again, our Russian and European friends, mathematicians, pushed the study even to a higher level so that we can enjoy what we're doing today. So lots of smart people came before us, and hallelujah for that, because otherwise we just maybe be struggling a lot more. So let's do an example of this. So these make really good test questions. And when you see them, it's like, oh, I'm going to nail this one. You know, it's, you don't have to start from scratch. So when you see this and you see a power of cosine or sine, you've got the limits here, you're done. So let's do this one. Sine to the 8th power x dx. So again, when you do these have to match up. Things have to match up, and the limits have to be this. Okay. So if you have to do a change of variable, whatever, that's fine as long as the new limits are these. If they're not these limits, this doesn't work. So it's got to look like this. Okay. You can't alter this. I mean, when you're ready to integrate, see, this one's ready to go. This one fits the pattern exactly. If I had a coefficient here and that was different, then I would do the change of variable. And then as long as what I ended up with looked like that or looked like this with the sine instead of the cosine, I'd know this applied. So make sure that you have this set up with these limits. Otherwise, it doesn't work. Okay, that's the thorn in your side here. That's the big if, so to speak. So now notice we'll say use Wallace, like Alice, use Wallace formula. Notice here that we've got the right limits and n equals 8. Okay, so use Wallace. So basically, that's this one right here. So remember, these are true for sine and cosine. Now, of course, look in my lecture notes on Blackboard and you'll see more about this. Now, when we think about this, we go to this formula and we just start moving up. Notice n minus 1 is 7, so we're basically going to stop there and then jump to here. So we've got 1/2, 3/4, 5 over 6, 7 over 8. So now notice this term is the n minus 1 over n, right there. And so now we end with this, times pi over 2. Now, of course, the rows up top are odd and the rows down below are even, and you're thinking relatively prime, but we see that we get some absorption here. So let's do 1/2 and just flip these around, 3 over 6, and then 5 over 4. Just do an interchange with these two, and then 7 over 8 and pi over 2. So what I did is I just basically said, okay, let's just go ahead and interchange these so we can enjoy the fact that this will give us a 1/2, this will absorb. So occasionally you'll get some of that, but not a lot. So now we have 1/2, 1/2, 5 over 4, 7 over 8 times pi over 2. Now, if you look here, and this is what's neat about this, these are really nice numbers. Notice here we have a, let's see here, what can we get out of this? We've got a 2, we've got this 2 here. So let me run these over here. Let me do this. Let me rewrite these and just kind of stick the pi off to the side. So I'm going to pull this 1/2 over. So we're going to have 1/2 times 1/2 times 1/2 times 5 over 4 times 7 over 8. So just go ahead and pull the 1/2 over and then pi here. Now notice, this is very interesting here. We have an 8 and an 8 and a 4. So we've got a 64 times a 4 and 5 times 7 up top. So just group it so it's easy to compute. So we have 8 times 8, 64 times 4 pi. And then, of course, that's just 16 times 16. That'll give us a 256. So we get 35 over 256 pi. Now, just like I said before, if you had to work this out with the with the reduction formula, kind of a long process. We saw how long it took for power 4 when we were doing 0 to pi, and we didn't have a, you know, we didn't even have a formula that we could have used. But as the powers jump up, you've got to apply the reduction formula that many more times. So as you jump up to 6, then you're going to have to apply it not only 2 times, but an additional time. It jumps up to 8, an additional time. And then you're thinking, you're going to raise the power reducing identity for sine squared to the 4th power? Insane. Not even worth it. That's why the reduction formula process that we get from integration by parts is basically a clean machine to take care of these powers. And of course, if we've got odd powers and a sine hanging out with a cosine, how simple. That's just a calculus 1 integral. The even powers are just a curse. They are a curse because they're just so much more complicated. And that's why we do really love these formulas here. They make our life a lot easier. So enjoy this. And of course, these make a nice quick test question. And of course, with your reduction formulas, ladies and gentlemen, put these down. Put these down. You need these. Now, you work with these several times, you'll commit them to memory, but put these down on the card so you can have as a reference when you're doing your quizzes and your testing. And of course, if you use this, when you're using this to do your write-up, then I need to see this. I need to see this work. I want to see the work. I want to see your calculations. I want to see what you are doing. Okay, that's very important. Now, well, let's look at some examples where maybe we could use a reduction formula or not. In this case, I think I'm going to use reduction. So here's another example. And we want to make this table ready. I like the table ready part with the U's. So here we've got the 5th power of tangent. How interesting, right? X over 14. we've got a real interesting argument, dx. Now, we have a reduction formula for tangent. Now, in certain cases, what you could do is you can pull off a couple of powers, a tangent, and then write it as a secant squared minus a 1. And of course, secant squared is the derivative of tangent. Add 1, divide by the new power. That's okay. But let's since we bothered to write down the reduction formula, let's use it. So, you know, you can try the peeling off the powers just like you'd have to do if you prove the reduction formula. So let's go ahead and use the reduction formula. Now, before we do that, ladies and gentlemen, I'm going to write it down so we can follow it. Let's go ahead and make this ready. Let's put this into table ready form with a u. So now u is equal to x over 14. I do think about this, ladies and gentlemen, and I do think about ways to make your life easier. But there are many opportunities in the calculus sequence to forge your own trail, put your own signature, but you've got to practice and you've got to put in plenty of time to master this material. So now what's du? Du will just be, well, here we go, 1/14 dx. So that's just the opposite of what we usually get. Now we're going to need to clean this up. So we need a 1/14 here. So we're going to have to pay for it with a 14 on the exterior. So that's interesting. Usually it's just the opposite. And so we have 1/14 dx. Now, like I said before, it's nice to go ahead and convert this to the new variable so you can easily apply the reduction formula without having to worry about carrying this along. You can, nothing wrong with it, but I think it makes the process easier. So now we have 14, which is kind of a thorn in our side, tangent to the 5th u du. Now, remember with this, when we get to the end of the problem, we'll do the interchange. We'll replace u with x over 14 because this is an indefinite integral. So we can't forget whence we come, so to speak. This is going to be part of our life once we complete the process. Now let's write down the reduction formula. So let's just write it down. Use the following. So I'll write this down. Tangent nth power du. Again, this will be tangent to the n minus first power u over n minus 1. So this one varies a little bit, minus the n minus second power of tangent u du. So this, again, we have at our disposal. Basically, it's just, okay, it's the integration by parts where you use the Pythagorean theorem. So again, this clings to the fact that the derivative of tangent is secant squared. So when you try to prove this, you can use that fact, just like we did with the powers of sine. So now notice we have n equals 5. So let's move it forward. So now what we want to do, and I will say this, when you apply these reduction formulas, stay true to the formula. Don't err from it. Don't vary from it. So remember, we've got the 14. So this equals 14. Then use your bracket. So now we've got tangent to the 4th power, u, 4, right there. So there's the first. N is 5, so we get 4 and a 4, minus. Now we subtract 2, so we're going to get a 3. So we have tangent to the 3rd u du, right there. Okay? You know what's interesting about all of this, and what's fun with this in particular, is that when the numbers are easy, it's just too simple. So now we look, okay, this one's fixed right here. This one we're done with. But this, again, we'll apply again with n equals 3. So apply again. So this means apply reduction. So now let's go ahead and multiply it out. So we have what? 14 over 4 tangent to the fourth u. Now we've got minus 14 right here, bracket, apply reduction. So n is 3. Go to the formula. So we have squared 2 minus. Now, of course, if n is 3, 3 minus 2 is 1. Wow, that was quick. So now when you look at this, it's like we're home free. We know the integral of tangent. That's calculus 1. That's a du over u. So now we've reduced this to a triviality using the reduction. Now let's finish it off. Well, of course, here we've got a 14. So that's a 7 times a 2 times a 2, tangent fourth u, minus, now notice here we have minus 14 over 2 times tangent squared. And here we have a minus minus. So this is plus 14 tangent u du. That's just kneading it up a little bit. Now let's finish it off. The 2's absorb. That gives us 7 over 2 tangent to the fourth u minus 7, negative 14 over 2 tangent squared. And then, of course, here we have what? Plus a 14. And then we know the antiderivative is we used this last class, the negative logarithm of the absolute value of cosine u. And then, of course, you can just tack on the constant. Now, of course, this is an antiderivative relative to the new variable u. But of course, when you do your Webassign problems or you do any calculus problem, Webassign doesn't matter, you know, whatever homework system you're using, we need the original variable. So now we just replace the u with the x over 14. Remember, with the definite integral, we don't return to the original variable because we're computing a number. So when we have the indefinite case and we've used reduction and we've switched everything out, it's good to go back to that. So now we get what we need, 7/2 tangent to the fourth, x over 14, or put more parentheses to the fourth, whatever, however you want to write it, minus 7 tangent squared, or tangent of x over 14 quantity squared. And then, of course, we have minus 14 natural log cosine of x over 14 plus a constant. So when we look at this particular problem, we see how efficient the reduction process is. Again, I want you to be comfortable with the fact that these particular formulas are easy to use. And you can, and again, when you prove them, you use the Pythagorean identities that you would use if you didn't apply this formula. It's done the same way. So I'm giving you the option, but I think I found that students have more success with this. And of course, it takes you to the next level. The idea is to perform the calculation so that you don't make myriad mistakes. And the only thing that we have to worry about here is keeping track of the n. So this educates you in using an integral table. And then, of course, you follow the recursion, you follow the procedure again. So it's very systematic. Okay? Now, let's look at an example where we just kind of beat it to death using plain old trigonometry. That is, we don't necessarily have a power of one trig function. We've got mixing and matching. So here's a good example. And then I want to do, let's see, I'll use maybe an integration by parts and do some product to sum formulas. Sometimes what we find is that integration by parts is so powerful, but there might be products that we can avoid. Like remember when we did the first problem with the cosine squared and we did it by parts, then we did the power reducing and the power reducing was a lot quicker. We might find that the use of product of sum formulas from trig might be easier than having to go at it with the what? Integration by parts. Of course, if we have to apply it twice, that can be very long. So sometimes we have to be particular in the methods we choose, because even though one we know is very reliable, it might get a little bit long. So we may have to just modify how we approach it. So let's look at another example. Here's another indefinite integral. So we have tangent. So this is kind of back to the old school. Tangent cubed of 2t times secant cubed of 2t dt. Now, this is where we look at this and say, well, Professor Ron, we don't have a reduction formula for this, but you're thinking, you know, with the way this is set up with these odd powers, we're thinking we've got some flexibility here. But let's just look at this. If we try to write this integrand in terms of secant, as long as we siphon off the derivative of secant, which is secant tangent, then we can actually look at this problem as an add one divide by the new power. So this is where we have to think about the calculus of the secant function. So what I would suggest here is making this into a Pythagorean identity problem using the calculus of the secant function. So here's one thing we can do. Pull off a power here of tangent and a power of secant. So this is kind of like intuition without the reduction formula. So we have tangent squared 2t, secant squared 2t, and then I'll put a little dot here. We'll say secant 2t tangent 2t dt. So when we look at this, we're thinking, oh, okay, so that's the derivative of secant, but we still have a tangent. So we're okay. We just want to replace this with the Pythagorean identity. So let's go one more step. So we're going to say tangent squared is secant squared minus 1. Tangent 2t. So notice here, and let me just write this down. Remember, 1 plus tangent squared u equals secant squared u. That's the Pythagorean identity. So tangent squared is secant squared minus 1. So now if we multiply this out, then we can make it table ready. So we've got, let's see here, secant to the 4th minus secant squared and then we have our secant 2t tangent 2t. Now at this point, what we want to do is to rig this. So if you think about this, here the u is the 2t. So we need a 2 in the differential. So if we think this, we don't have to change the variable, but just like we normally do, u is 2t. So du equals 2 dt. So we need that factor of 2. So let's go ahead and make it table ready. So this will be 1/2 secant to the 4th 2t minus secant squared 2t times 2 secant 2t tangent 2t dt. So now the derivative of secant 2t is 2 secant 2t tangent 2t. So this is table ready. So again, we think about fixing the argument here, and now both of these are ready to go. So just remember, we've got the derivative here, except we're lacking the factor of 2. So we've got to look at this as an adjustment, and then we can go break it up and do add 1 divide by the new power. So now I'm going to break this up into 2 pieces, even though I don't have to, just to make it a little clearer for you. So this is going to be 1/2. You could just say we're done, but let me just break it up into two pieces. I'm just putting a little more detail here just to make sure we all get what Professor Ron is doing. 1/2. So now we have the power of secant times its derivative. The power of secant times its derivative. Add 1, divide by the new power. So this gives us 1/2, excuse me, times 1/5 secant to the 5th 2t minus 1/2, and now we're going to add 1 divided by the new power, 1/3 secant to the 3rd 2t plus a constant. And so now this will give us 1/10. Of course, you could factor this, but we're fine with this. Secant to the 5th 2t minus 1/6 secant to the 3rd 2t plus a c. So this is kind of, in this particular case, ladies and gentlemen, this is kind of the standard technique for dealing with trig integrals. But what we're seeing here is that this wasn't the standard just single power of a trig function. We could mold it into that, but we're finding here that if we use the derivative of the secant function and then the Pythagorean identity, we can reduce this to add 1 divided by the new power. Now, of course, once you get to this point here, you could just jump from here to here. You don't have to write this step. You can just say, well, there's a power of secant, there's a power of secant, there's the differential, good. You don't even have to break it up. You could move from here to here and leave out this step. I've tried to add more steps here to make sure that everybody sees the process. And so I don't want you to jump at this and try to be at the finish line too soon. When I looked at some of your work, you'd write something down, then you jump to the finish line miraculously, which is like, okay, that doesn't make any sense. I have to be, if you did this problem and you left out that step, that'd been completely clear to me that you understood the logic. Okay, so don't just write something down and like, well, just make Professor Ron happy. No, that's it's not to make me happy. The purpose is to train you so you can become a STEM professional. My goal is to give you techniques so you can get better at this. It's not a trick and it's not fun. This math is not fun. If anyone told you math should be fun, it's not. Math is hard work. When is it fun? When you understand it and you take that understanding and you make good grades. Okay, that's the fun part. You know, it's like anything that you do well is difficult. The rewards come when you accomplish what you want. And of course, if you're doing what you love to do, you will always do your best. Okay, that's the fun part. I think we oversimplify STEM education. We oversimplify all education. I think that's the problem with education these days. So let's make sure that we're focusing on the strategies that move us to the next level. Okay, now what I want to do, just kind of as a little breather, then I'm going to come back to an integration by parts, though you're probably thinking you could leave integration by parts on the side of the road. Let's look at an example, kind of like this last one, where we have a product of 2 first-degree trig functions in sine and cosine. Say we're doing Fourier integrals and PDEs, and we're like, oh man, I want a quick way to do this. So let me show you an example here. Here are some formulas that are useful. These are called the product to sum. They're easy to derive using the sum, the addition, and subtraction formulas, but I want to write them down for you. And you can also see these in the lecture notes. I give you lecture notes in the video, and then there's some posted lecture notes that you can also work through. And I know a lot of you work through them because I can see it in your work. I can definitely see it in your work. And I'm glad you do that because that's there for you. So now I'm going to use A's and B's. So sine A cosine B, and of course you could flip these around, you could do the cosine A sine B, but that's redundant. Just flip them around and use the B and the A, it doesn't matter. 1/2 sine. Try to make these user friendly. When I teach pre-cal, I use uppercase letters and then U and nu so that my students can see the difference. So we might be thinking that if we had a product of sine and cosine, then instead of using integration by parts, which would be a little bit two applications to repeat, we can just go ahead and write the product as a sum, and these are easy integrals, or easier, much easier. And then, of course, we could have a product of two cosine functions with different arguments. Of course, if the arguments were the same, we're back to what we've been doing. So 1/2 cosine A plus B plus cosine A minus B. This is just using the sum and addition formulas where you add and subtract them to eliminate terms, which is what you did in pre-cal. You should know how to derive these. It's very simple. And then sine A, sine B equals 1/2, and this has all the minuses in it. I always tell students, remember the minuses for the sine. Cosine A minus B minus cosine A plus B. Because the sum formula for the cosine function is kind of quirky. It has a minus in it, which is very counterintuitive, but it's just the nature of the cosine function being an even function. So what we can do is say that instead of actually integrating the product, which would require parts, which we love integration by parts, but it would be so much easier to keep track of A and B and then use these formulas, and sine integrals and cosine integrals are easy. Those are simple. That's what we learned back in Calculus 1 because we learned the derivatives. So we would prefer this. So in place of this, use this, product to sum. So here's a nice example that's a definite integral that's going to remind you that we're back in a pre-cal class. So I'm warning you now, it's kind of like this is a good problem I do in pre-cal when I'm teaching them about reference numbers in the unit circle. So if you feel like you're in pre-cal, that's good. I'm going to teach it that way. So we have sine 6x cosine 4x. I just take these problems and change them up a little bit. And I actually saw this one in your textbook, and I thought this was a good example. But I didn't change this one. I just wanted to make sure that this would give me the good example that I wanted. Now, notice here, we've got sine 6x cosine 4x. This is a definite integral. And we don't want to use parts. So we look at this and say, let's do the alternative here, because even though this is going to take a fair amount of arithmetic, wouldn't it be a lot easier to not have to apply integration by parts twice, because this will repeat after two applications. This will convert to a cosine, and this will convert to a sine. And then you'll get back to the sine and the cosine with the second application. So you get a sine 6x and a cosine 4x after two applications, which is a fair amount of work. This should be quicker. So now what we want to do is just, in the book, they use little m's and little n's and x's and stuff, and that's a little bit much. So what I'm going to do is say A equals 6x right here, and B equals 4x. So if you use my notation, it might be a little bit easier to use. And so now this will give us the integral pi over 6 pi over 3. Now we're going to use this formula here. So we'll have 1/2 sine. So we'll have 6x plus 4x plus sine. And of course, you know the sine function is odd, cosine is even, so you could use that if you needed to. 6x minus 4x dx. So when you look at this, we're thinking, okay, this is easier, a little bit of arithmetic involved. So we've got a 1/2, which we can factor, pi over 6, pi over 3. And now, of course, we have sine of 10x plus sine of 2x. So when you look at this and you think about this particular calculation, you're thinking, boy, we're going to be multiplying these numbers, and then we're going to have to use reference angles and reference numbers from pre-cal, but that's fine. These are still doable integrals. So now we want to make them table ready. So let's do that. So first, we're going to have 1/2. And then, of course, we have a 10 here, so that's going to be a 10 dx. So we're going to have 1/10 pi over 6 pi over 3 sine 10x times 10 dx. Make that table ready. That's table ready. And then plus 1/2 pi over 6. Oh, well, let me not be too quick. Go ahead and do what I did on the last one. We have a 2 here, so we're going to need a 1/2 with the differential. So we have, well, of course, now I've got to move this over. So we've got pi over 6, pi over 3, and this will be sine 2x times 2 dx. So these are both table ready. Now, of course, the antiderivative of the sine is the negative cosine. So now we do this, so we get equals what? 1 over 20. And this will be what? Negative cosine 10x evaluated pi over 6 pi over 3, then plus 1/4, and then we'll have negative cosine 2x. The fun never stops, right? Pi over 6 pi over 3. So now when you look at these problems here, you're thinking, okay, now this is a good Cal 1 problem. So if we had just started with this right here, or say this problem here, that'd been a good Cal 1 problem and a useful Cal 1 problem to remind everybody why you learn trig. You can see with what we've been doing today that trig has been indispensable. So now let's go ahead and apply the fundamental theorem. We've got the negative 1/20. So this is negative 1/20. So we have cosine. Now, of course, notice we're going to have a 10/3 or 10/3 times pi. So 10 pi over 3 minus, now we got pi over 6. So that's going to be cosine 10 pi over 6 plus 1/4. Oh, now I'll just stick the negative here, but let me just go ahead and put it out front. That way we can really see it. So we got the minus. So now, of course, we're going to have cosine 2 pi over 3 minus cosine, and then we have 2 pi over 6. So let's see what this gives us. So we have negative 1/20. Now we want to think reference angles. So here, notice, let's just go ahead and write this out. So this is cosine. So 3 into 10, that'll go 3 times. So that'll be a 3 pi plus a pi over 3, right? Okay, so they were doing a little bit of pre-cal. Minus, and now we have cosine. So of course the 2's will absorb. So we have 5 pi over 3 minus 1/4. Now, of course, we're in a domain here that we actually understand. We can figure out these, but this is pi over 3. Its reference angle in this case is pi over 3. So this will be the negative of cosine of pi over 3. And this is just negative cosine of what? Pi over 3. Again, this is in the second quadrant, so the cosine is negative there. The reference angle is pi over 3, so this is negative cosine of pi over 3, and that just is what it is. So now here, this gives us negative 1/20th. And now, of course, 3 pi is congruent to pi, so this is going to be 4 pi over 3, so this is cosine. Now, well, let me just say this. When we look at this, let me write this way. Let me just do a little sidebar. Remember, 3 pi plus pi over 3 is congruent mod 2 pi to pi plus pi over 3. And so now we have what? We've got a 3, so that's going to be a 3 pi plus a pi. So this equals 4 pi over 3. Now, what's interesting about all of this, you know, when we think about what we're doing here, and when we think about how we do all of this, we're all treating this problem in terms of pre-calc. We've only done calculus right here. And so now all of this is just pre-calc. So at this point, we've got what? Cosine. Let's go ahead and write this in. 4 pi over 3. And here we've got cosine of 5 pi over 3. Now again, this is actually in the fourth quadrant. So let's write this down. So notice 5 pi over 3. And that'll give us what? A 2. So when we divide, well, let me just write this way. Let's see where this actually is. So this will give us a pi plus a 2 pi over 3. So that takes us back around to the fourth quadrant. So when you subtract, in this case, 2 pi, so the reference angle, so we'll say theta hat will be 2 pi minus, so just doing a little trig here, plus 2 pi over 3. So this is going to be pi minus 2 pi over 3, which is pi over 3. And of course, in the fourth quadrant, the cosine is positive. So this will be the same as cosine of pi over 3. Now, for the 4 pi over 3, let's do that. 4 pi over 3 equals pi plus pi over 3. And that's in the third quadrant. And so the reference angle here is just this minus pi over minus pi. So this is pi over 3. But notice in the third quadrant, the cosine is negative. So this will give us, let's go ahead and write this down for the next level, 1/20th. This will be the negative of cosine of pi over 3. So we can go ahead and take care of that. Now here, we're done with this part. So pi over 3, that's what? 1/2, 2 negatives. So we have minus 1/2 minus 1/2. So let's go ahead and write this down. So this will be minus 1/4, and that's just a negative 1. And let's see here, what else do I have? And then here, let's see, what do we have? Equals. So we've got all these negatives absorb. So this is negative 1/20th. And here we have a negative 1/2 minus a 1/2. And so this is going to be plus a 1/4. So here we've got let's see, in this case, 1/2, 1/2. So this is a positive 1/20. So this is just a negative 1. So we have 1/20 plus 1/4. This goes on forever. And of course, we have a 20. So this is a 1. So that'll be a 5. 4 into 20 is 5. So this is 6/20. And we can divide by 2. So that will be a 3/10. Now, the reason I thought this was a good example is that when you tutor your friends in pre-calculus, you can say, okay, well, you can either memorize the unit circle, or you can actually compute via reference numbers and reference angles. And so this is what you do when you tutor someone. You say, well, where is that? Okay, well, you figure out where these lie on the unit circle, and then you write the reference number, and then figure out, okay, well, in the fourth quadrant, the cosine is positive. So we have, in this case, here, we don't change the sign. We get cosine pi over 3. But now, of course, with this one, 4 pi over 3, that's in the third quadrant. So we have to take the negative of cosine of pi over 3. So this is a nice review of your pre-cal. So let me just state this. Had we not had to do the definite integral, and we'd have just stopped this problem, say at this point, we would have had these two integrals here with no limits. That would have been fairly quick. But could you imagine having to do this problem with two applications of integration by parts, and then keep your fingers crossed that you didn't make 5 or 6 mistakes, and then work through this? So the key is, when I see a problem like this on your test, I need to see the computation. I need to see the computations so that it at least lets me know that you know your pre-cal. Trigonometry is an art form. Trig is just as hard as calculus, easily. And when my pre-calculus students moan and groan about it, I said, that's okay. There's plenty of work here. I said, but this trains you for calculus because it makes you sharp. So what we're seeing here is that by utilizing the product to sum formulas, these products of sine and cosine can be made very simple. And so we get very simple integrals. But if we have a definite integral, then we may have to use a little bit more of our unit circle and trigonometry. But I love this problem because it is an elegant application of your unit circle. And I do problems like this in my pre-cal class, where I'll say, well, just, tell me what this line is. I'll just write down a line from a calculus problem where it's all pre-cal, and I'll say, compute this. And they say, well, this is a lot. I said, well, get used to it, because when you get to calculus, you will have to do this. So what I try to do in pre-cal is to teach them the type of pre-calculus that they're going to have to use in calculus, and it does help them. Okay, so good. So now you know how to treat these. Put these on your note card. Okay, put these on your note card and master this problem. This is an excellent problem. If you can do this, you can do any of these. Now what I wanted to do is another example using our techniques with integration by parts. And also there was an example, this is a good one. Let's do an integration by parts example that kind of falls off the beaten path, in the sense that when we look at it, we're thinking, if I could get rid of one of those squares, this would be an easy problem. So what I want to show you is that now we can use a power reducing identity with integration by parts to effect a nice solution using the shortcut method. So here we go. So example. So we've got x squared. Now if this were just plain old sine x, you'd say we're done, but I put a square there. So you look at this and say, okay, Professor Ron, I think I can do this using the method you taught us last time. We know it's integration by parts, but this is not undoable. If we use the power reducing, knock it out, we can differentiate the x squared to 0 and just use diagonal lines. And then we're like, oh, okay, this is doable, because even though this integral is not the easiest integral on the block, it's certainly doable using power reducing. So notice, if this were just plain old sine x, you knock it out in no time, because you just have the dv being the sine and just integrating that over and over until you zero out this column and connect integration by parts, 3 applications. So the idea here is that if we take what we learned last class with a slight modification of the trig integral that we learned how to do, then we're good to go. So let's use integration by parts. So first, we'll say D. Well, let me give myself a little bit more room here. Always give yourself room. I like when you all spread out your work and I could see it clearly. That was really nice. I really appreciate that. So we have an x squared. And over here, let's look at a sine squared. So this would be the sine squared dx. So we'll say, okay, well, this is u equals x squared, but we're doing it more informally. So don't put in the u's and the dv's because we're going to use the table to select the next u and dv. So don't clutter it up with all that stuff. So now you're thinking, all right, well, Professor Ron, I can do this. This is 1/2 minus 1/2 cosine 2x. That's the power reducing identity. And I can integrate that because I took calculus 1. So now first, let's just think about this and then make it a table ready. So first we've got the 2 here. So this is going to be what? 1/2. Now we're going to need another 1/2. So that's going to be a 1/4 cosine 2x. And then I'll again, let me just go ahead and throw in the dx here. Since I'm going to put it in here, just throw in the dx. That way you can see what I'm doing. Only doing this here so it's easy for you to see. And then here we have the 2 for this one. This is by itself, 2 dx. So when we make this table ready, the 1/2 is just the 1/2, but now this is table ready, so I can just do the sign. So when I antidifferentiate the cosine, I get the positive sign. So I need that 1/2 times the 1/2 to pay for that 2. So now this will give us what? 1/2 x minus 1/4 sine 2x. So the idea here is that when you make this part table ready, this is table ready, you go directly to this. And let me make sure you can see that 2 there. Here's that 2, okay? So table ready. Now we differentiate this, 2x, okay? So apply it again. We'll do the easy part. Derivative here is 2. Now anti-differentiate. So now we're going to add 1, divide by the new power, 1/4 x squared. And now, again, we're going to need another 1/2 here. The antiderivative of sine is the negative cosine. So this will be a plus 1/8 cosine 2x. So again, we need the 1/2 again, like we had up here. I did it here to kind of give you the idea of what we can do. And now we can just do it because we understand the process. And then one more, 0 out, add 1, divide by the new power. So this will be 3 times 4, 1/12 x cubed. And now do the same thing again. The antiderivative of cosine will be the positive sign, but of course we have the 1/2 from the differential. So this will be plus 1/16 sine 2x. So what I want to point out here, which is very important when you think about this problem, is that due to the fact that we have the square here, the problem is more difficult, but still doable because the integral is doable. I mean, you normally don't want to have to work too hard over here, but if it's doable, that means your choice for the dv was acceptable. Okay, it's just like I say, you know, your work is acceptable, it's not acceptable. It's unacceptable if this integral is basically as hard as the original one. That's no good. Okay, so we can do this and we're good. So now, remember we did one pass, we new u and new dv right here, apply again. New u, new dv, apply again. But now when we cross, we zeroed out. So all we're left with are the diagonal lines. So this Oliver Heaviside method, when you've got a simple polynomial here, is miraculous how it ties together the additional iterations of integration by parts by using the selection process here that you've already made without having to write the integral down again. And so here we have what, 3 applications, which we easily see, and you can easily go back through here and check your work. And now we do the diagonal lines, plus, minus, plus. And there's your answer. And then we'll just neaten it up. I like how some of you didn't bother to go back and clean up that problem I did. You just entered it in your WebAssign. I'll check on your work. And I said, good for you. I said, if you don't want to neaten it up, you don't have to. But if I put it on the test cleaned up, you'll have to do the algebra. So sometimes that makes you do a little bit more work. But good for you all who move forward with your homework. So now we can go ahead and multiply out. So we have x squared. So that's going to be a 1/2 x cubed and x squared here. So we get a negative 1/4 x squared sine 2x. This is a really elegant process. We're hats off to Oliver Heaviside. So x squared here, giving us the negative 1/4 x squared sine 2x. Now multiply by 2x. Now notice the 2 and the 4 will absorb. So that's going to be a 1/2. So 1/2 x cubed, and 2 here, 2 over 8, that'll be a 1/4. So we get plus x 1/4 cosine 2x. Now, what's interesting about this, and of course, and notice here, you see, Professor Ron, you just ignored that negative here. Let me go ahead and stick it back in. That's why we always write everything down. I thought, well, I'm just ignoring the negative. I'm worried about the reducing the denominators, but look, put the negative here because the negative is what? It's right here. So now let's see, what do we have left? We've got, let's see, we've got the 1/2 x cubed, and we've got the negative 1/4 x cosine 2x, and then the very last line with a plus. So plus minus plus 2 over 12, that's 1/6. 1/6 x cubed, and then 2 over 16, 1/8, plus 1/8 sine 2x, plus a constant. Now, this is pretty much cleaned up, but we haven't collected any terms here. So now with the cube terms, let's get all of our cube terms together. Notice these absorb. See, all of your work is clearly marked here, and you can go back and check it. Did I distribute the negative? Negative, negative. Here, positive, no change. Absorb, and then I've got the 1/6. So this gives us 1/6 x cubed. And then we have an x squared with the sign. There's only one of those. So that's minus. So let's check that off. And let's see, we've checked this off. 1/4 x squared sine 2x. Move on down. Just one of those. Hallelujah. 1/4 x cosine 2x. Check it off. And then one of those. Check that off. 1/8 sine 2x plus a constant. Now, and I wrote in my notes here, good example. Well, why is this a good example? Well, again, I've made a concerted effort to make sure that you understand integration by parts and how it impacts trig integrals in a way that should make your life easier. Again, if it's just a simple old, cosine and sine with odd powers, and you got the differential here, you learned that in Cal 1. That's simple. But the idea is we've got to be able to mesh the, let's see, where did I do that first part? Oh, it's on the same page. We've got to be able to combine the trig integral with the integration by parts. You're thinking, well, this would make a good integral formula. I mean, we could devise an integral formula with this. But here's the thing, ladies and gentlemen, when you look at this problem, you're thinking, I'm sure there's an integral formula for this to cut down on the work, but this is doable. This is doable. So for instance, if we get, you know, to a integral problem and you search the formulas that we have and say, oh, this one matches up with that one, I'm going to use this one. I would just say with a problem like this, at least this is a doable method that's reasonable. When you've got fairly straightforward algebra and a very systematic way to do the computation, that is an acceptable process. I can remember when I show my students how to reduce the sixth power of cosine with the power reducing, I shake my head and say, well, kids, I'm going to show you a quicker way to do this with a reduction formula for integrals. And they're like, well, so why are we doing it? I said, well, I've got to keep you busy and I want you to be able to do the algebra. But we're already seeing in the calculus realm, you can couple different techniques to make your life easier. So when you look through this problem, go back to integration by parts with the shortcut method and then compare and note how we use the power reducing identity for sine squared to affect these integrals, and then alternate the sign. Just like the horizontals go minus, plus, the diagonals go plus, minus, because of the minus in the integral formula for integration by parts. So again, very nice problem and a very powerful technique. We had no way of doing anything remotely close to this before. And now we've got a technique that's filling up the integral table, basically. Now, in closing, I want you to use as many different techniques that I've talked about as you do these problems, and use your Calculus 1 techniques too. But I want to show you that there are some problems that are actually pretty simple. And Dr. Larson will often say, well, you know, if you've got a integrand that doesn't look like anything, you know, so just simplify it the best way you can. So here's an example of that. And we've talked about this before. Say you had tangent squared x over secant x. And then you're thinking, okay, I showed you how to integrate secant cubed with integration by parts. But if you had something like this, you're thinking, okay, well, the first thing, this is kind of transporting us back to pre-cal. And then you're thinking, well, maybe this is a cal 1 integral, or maybe not. Maybe it's cal 1 and I just need to do some work on it. This is a cal 1 integral. But since we've been doing all this other stuff, you think you have to attack this with a difficult procedure. Well, of course, this is simple. We look at this and just say, well, I don't need a fancy formula. I can now just replace tangent squared like we did before with the Pythagorean counterpart, just like we've done in some previous examples. So now this will be what? Secant squared minus 1. I like how the WebAssign says, now this might be difficult, but it might be easy. So don't pull out the major artillery unless you need it. So now when we look at this, we're thinking, well, how simple is this? We live for this. So now we can rewrite the integrand by breaking up the fraction. So Pythagorean identity, and then of course we have secant squared x divided by secant x minus 1 over secant. But of course, the first term is just secant. And of course, 1 over secant is cosine. So we're thinking, wow, how simple. So when we think about what we're doing with trig integrals, for instance, you know, we might have some really, really simple integrals that don't require anything I've taught you, that you just use what you already knew, add 1, divide by the new power. But we often have to think about the calculus that we've learned. So now we go back to our cal 1 and say, well, we learned how to integrate secant. So this will be the integral of secant. Let me just write it out separately. Minus the integral of cosine. And of course, this is the natural log of secant x plus tangent x. And you all be careful with your pi's and your rhos when you do your work problems and center of mass. A lot of you miss the problems because you leave out the area density or you leave out the pi. It's unfortunate. Be very careful. And then, of course, the antiderivative of cosine is just the positive sign. So we get minus sine x plus a constant. So when you do some problems, you just say, oh, I know how to do this. So when you look at your WebAssign, ladies and gentlemen, there are going to be problems like, oh man, this is so easy. So don't look at every problem as being a major ordeal. If you have to use a reduction formula or a power reducing or integration by parts, go forward with it. If you have to use a product to sum, go forward with it. But some of the integrals will be quite simple. I mean, really simple. So don't confound yourself by trying to do major work or major operation on a very simple integral. And that's where, like I said before, doing lots of examples, practicing, going back through all the examples in the lecture, going back to my lecture notes on Blackboard, working through those, open up the PowerPoints, you'll see additional problems, work through them. Take out your pencil and paper and write and write. You need to be studying this class a couple hours every day minimum. And I say that because my most successful students have done the same. Now, everybody's like, well, I've got 1 million classes. Well, you know, you're a STEM professional. So remember that math is the bedrock of what you will be doing. Math is the cornerstone of engineering, obviously mathematics, finance, sciences, supply chain. People are now doing supply chain in the business sector. And you got to know your math and know how to code. I mean, that particular profession is just blown up with our COVID environment now. Supply chain is Amazon.com. I mean, it's amazing. There are so many wonderful STEM jobs that are waiting for all of you. So I want you to be first in line because you can do the math. So what I'll do, ladies and gentlemen, I will post another little blurb about the upcoming test. Again, this will be a shorter test in the sense that it covers less material, same types of computations. Go back over the solutions for the first test, work through every one of those problems just to make sure you've got the techniques down because they repeat with a lot of these problems. And then of course the integral problems, again, will be standard integration problems like you have in your WebAssign and what we've been doing in lecture. So again, go ahead and set yourself up for success. Practice, practice, practice. I like it. While some of you in the class have said, I have worked hard. And when I look at your work, I can tell. I can tell by the questions you ask. And I salute all of you. But just remember, write down all of your work and let me see what you are doing. And when you make your scans, they need to be clean so I can read them. And they have to support your work. If they don't support your work, again, you can't receive credit for a problem when your work is not supported. And so stay away from the computer algebra systems. If you've got fancy calculators or you've got websites that you're using, stay away from them. They will only make you worse. Remember, when I was in grad school, I had a very good friend. She was a visiting professor in complex analysis, and she would always say, stay away from the computer algebra systems. She said, the first time you get addicted to those things, you will learn nothing. She said, you will not even know how to add fractions. When I do computations, I do them by hand because it's great to have software. I'm not saying that's a bad thing, but when you're learning the process, you have to understand the process and then use the computing device when you need an approximation after you've done the work to an exact answer. So just remember that. There's nothing wrong with using a calculator. I'm not saying that. I'm just saying don't rely on a computer algebra system. So hallelujah, we have some warm weather. This morning when I was running, it felt like springtime, and I'm grateful for that. Let's not have any more of this winterized weather. I think we're done for it for the next 50 years, so to speak. But I appreciate your attendance this morning. I always admire what you're doing. I know it's hard. I'm always your biggest fan. Remember that. Of course, I'm the one with the whip saying work hard, but I'm going to root for you also. So you all have a great day. I'll have one session today, and then of course I have 3 on Thursday. So I will send out invitations for that. Everybody have a good day, and thank you.